Students, welcome to the third module of our subject refrigeration and air conditioning. So, students, in this module, we will be dealing with advanced vapor compression systems. So, students, the in the previous module, that means the second module, we have dealt with simple VCR system, right? Simple VCR means simple VCR system. It means it consists of one compressor, right? One compressor, one condenser, one expansion valve, and finally one evaporator, right? So if the number of units, the number of components in the VCR system are only one each, then such type of VCR system will be a simple type. Such type are usually considered as simple VCR system. So in simple VCR system, the low pressure vapor refrigerant from the evaporator is compressed in a single compressor, in a single stage or in a single compressor, and delivered to the condenser, and condenser at a higher pressure, and from condenser it goes to an expansion valve, and from expansion valve, which is the vapor refrigerant is expanded to its liquid form, and it is now fed to a single evaporator only. Okay, but students, in order to improve the performance of the system, or in order to improve the refrigeration effect of the system, or in order to improve the COP of the system, or in order to decrease the work in the compressor, or in order to make the system a little bit simple in size, we are adding or we are modifying the system in such a way that this VCR system becomes an advanced type. So that is the significance of advanced vapor compression system. So have you got the idea? So in order to improve the performance of the vapor compression system, we are upgrading simple vapor compression system to an advanced vapor compression system. So advanced vapor compression system may consist of different number of higher number of compressors, a higher number of evaporators or expansion valves and condenser. Usually there is only usually one condenser is only used in a refrigeration system, but the number of expansion valves or compressors or evaporators may vary with respect to the desired effect. Sometimes we may require to increase the refrigeration effect. Sometimes we may require to decrease the size of the compressor, or according to the priorities. There are different types of advanced vapor compression system, and and uh, and usually the advanced vapor compression refrigeration systems are classified into three. So first one is multiple compressor system, multi-stage compression system, multi-stage compression system. Second one, multiple evaporator systems are there, multiple evaporator system, multiple evaporator system. And third one is cascade system. So you will be learning all these three different types deeply in the upcoming sessions. So multi-stage compression system itself is classified into different types. Similarly, multiple evaporator systems are different type, and finally you will learn about cascade system and all. So, what is the need of in general? Why these multi-stage combustion systems are used? So, as an outline, I can tell you that if suppose Suppose this is the TS diagram. Okay. Suppose this is a inlet. This is the state of state of vapor refrigerant at the inlet of the compressor. Suppose this is the evaporator pressure. Suppose this is the condenser pressure. So if the condenser pressure is very high, so directly compressing from 1 to 2, okay, directly compress, sorry, okay, suppose suppose directly compressing it to 1 to 2, maybe little bit may make the compressor a larger in size. So because the pressure ratio is very high, means your compressor will be having a higher size, a larger size. Suppose if you are um, compressing this in two stages. Suppose this is an intermediate pressure intermediate. Suppose I am compressing it to 2 in one particular compressor and 2 to uh, 3 in another compressor. So here to here one compressor, here 2 to 3 another compressor. So I am compressing the vapor refrigerant in two stages to the same pressure. Okay. So I am compressing, the final output pressure is PCP, condenser result, but I am compressing it in two stages. So if you are compressing it in two stages, means you can use two small compressor instead of one very large compressor. Okay, so that is the idea of applying this uh, advanced vapor compression system, or using this advanced vapor compression system instead of simple vapor compression system. So we'll get a detailed idea in the coming sessions. So in today's session we will be dealing with some types of multi-stage compression systems. So there are so there may be uh, so there may be confusions now why this type of advanced compression systems are used, but I hope you can clarify all those doubts while we proceed with the details of these systems. The first one, so this is so we will deal with multi-stage compression system, multiple compressor system initially. Multiple compressor systems initially. So there are different types of multiple compressor system, and first one is two-stage compression with the liquid intercooler. So here we have two-stage compression with the liquid intercooler, means there are two compressors. Okay. So here is the schematic diagram representing the working of a two-stage compression with the liquid intercooler. So suppose we have two compressors, right? So this is our starting point, one. Okay. So this is a one. Suppose the from evaporator the dry vapor refrigerant is fed into the low pressure compressor. So you can see in your pH diagram. So this is one. Okay. So from 1 to 2, the vapor is compressed to an intermediate pressure. So 1 to 2, you can see here 1 to 2. Vapor is compressed isentropically to an intermediate pressure P2. Okay, to an intermediate pressure P2, and this P2 is fed into a liquid intercooler. Because at 2, what is the state of the refrigerant? It is gaseous in state, right? So this is a superheated. So you can see here it is a superheated vapor. This superheated vapor is fed into a liquid intercooler. So what will happen if the superheated gas is fed into an intercooler? It will definitely lose some of its heat and becomes a little bit cooler, right? So its temperature will get a decrease, but the process will be constant pressure process. Most of the cooling or heating takes place in constant pressure process. So you can see here from 2 to 3 it will get, so 2 to 3 what will happen, it gets cooled, right? So you can see here from 2 to 3 it gets, the temperature decreases but the pressure remains constant, and at 3 it again reaches back to the dry saturated condition. So at 2 it is superheated condition, at 3 it is dry saturated condition. So how is this superheated vapor is cooled? This superheated vapor is cooled using the liquid coming from the condenser. Okay, so you will get idea soon. So look at this path of this referent again. So 3 to 4 what is happening, 3 to 4, 3 to 4 it is again compressed to a higher pressure, so or the condenser pressure. So 3 to 4 it is compressed isotropically to the condenser pressure. So this is a high pressure compressor, this is the low pressure compressor. Because why this compressor is known as low pressure, because it is compressing from the lower pressure to an intermediate pressure. This compressor is compressing from intermediate pressure to the higher pressure. So this is HP compressor, this is LP compressor. Okay. now from 4 Now from 4 what is happening? From 4 it passes through the condenser and it reaches 5. So 4 to 5 is condensation. So it is condensed up to the point where the high pressure the high pressure high temperature vapor gets converted into the liquid form, saturated liquid form. So here it is saturated liquid form. So from 5 it enters an expansion valve. So this is an expansion valve. So there are two expansion valve here. So this is first expansion valve. So in first expansion valve it isenthalpically expands, its pressure gets reduced. So its pressure get reduced. Okay. And this reduced pressure, the liquid vapor whose pressure is reduced to an intermediate pressure. So this is intermediate pressure. So up to that intermediate pressure the pressure is reduced and it will be in liquid form, right. So this, after expansion the vapor will be in liquid form. So it will get collected in this liquid intercooler. So it will be in liquid form. Its temperature will be lower than the refrigerant coming from the low pressure compressor system. From the refrigerant from the low pressure compressor system will be coming with a very high temperature and high pressure, right. So it will be in superheated form. So this low temperature liquid will absorb heat from this superheated vapor coming from the low pressure compressor. Okay. So after absorbing heat from this superheated vapor, some of this will get evaporated. Some of this liquid will get evaporated, right? You can see here some dots here, right? So these are nothing but the evaporated liquid from the liquid intercooler. Have you understood what is happening here? So here I will show you another. Okay. So here you can see that from a low pressure compressor heat superheated vapor is coming. From expansion valve low pressure low temperature liquid is coming. So this liquid will uh, extract heat from this superheated vapor. So heat is extracted. So heat is added to this liquid. So what happens to this liquid? This liquid gets evaporated. That is why you can see here some hatched portions, right? These hatched portions represents evaporated liquid. So this evaporated liquid gets added to this superheated vapor, and the mass of the superheated vapor will get increased because some of the evaporated vapor joins that stream. Okay, so this will pass to the HP compressor. Okay, now what happens? So the mass will be reduced. So the reduced mass pass through the second expansion wall. Then it again gets expanded. So you can see here from 5 to 6, it again gets expanded to the final evaporator pressure, and in that state it will enter the evaporator, and from evaporator the refrigeration 6 to 1 is the refrigeration effect. The heat will be absorbed from the refrigerating the space to be refrigerated. Heat from that space to be refrigerated will be absorbed by the evaporator, and again it will, and again the process will repeat, right? So you can see here some of the mass will be bypass here, right? Because some of the mass is added with the superheated superheated vapor. You can see here, so some mass is coming from here, some mass is coming from here, so both the mass will get added and this mass will pass to the high pressure vapor. Okay, suppose here the mass is m1, so m1 reaches here, again m1, m1. Okay, suppose, so here also m1. So some evaporated liquid, maybe that evaporated liquid mass will be m3. So m1 and m3 gets joined together to form m2, right? So m1 plus m3 equal to m2. m2 m1 is the amount of refrigerant passing through the low pressure compressor. This low pressure compressor mass, the mass of mass passing through the low pressure compressor is joined with the evaporated liquid from the liquid intercooler. Let that mass be m3. So m1 plus m3 will be m2. This mass will pass through the high pressure compressor, and it will again pass through the condenser and then expansion valve and reach liquid intercooler. So in liquid intercooler, m2 ends. The mass entering the liquid intercooler will be m2, but m2 minus m3. So some m3 will be lost, right? This m3 is lost. M3 is lost as evaporation, and m2 minus m3 equal to will be what? M1. So this remaining m1 passes through the expansion valve, and this m1 again continues the cycle. So this is what happening in that system. So you have to be very sure of very sure of the amount of refrigerant passing through different compressors and the expansion valve and all, and what amount is lost as the evaporation, lost in the form of evaporation in the liquid cooler. So such things you should be aware of. Okay, so in this figure you can see m1 here. From here in this direction m3 is coming. So at this point m1 and m2 joins, and m1 and m3 joins, and to form m2. This m2 come here and reaches here, and from m2 some m3 is passing through this direction, and remaining m1 passing this direction. So this direction m1, and this m1 reaches here, m1 goes here, and this m1 reaches here, and m1 is again joined with m3 plus m1 again m2. So the cycle repeats. Okay, hope you have understood the concept. Okay, so students, how to calculate the refrigerating effect in this particular cycle. So refrigerating effect is nothing but this area, right? So this is where refrigerating effect is taking place. So refrigerating effect is nothing but H1 minus H, what, H H6, right? So enthalpy of H6. So this is kilojoule per kilogram, right? So kilojoule per kilogram. So if you if you multiply it with m1, you will get so this is kilojoule per kilogram minute because this is m1 dot. Okay, this is rate. Okay, mass flow rate. So if you add m1 dot into h1 minus h6 means this kilogram gets cancelled, and therefore it will become kilojoule per minute. Here, the answer will be in kilojoule per minute. Okay, if m1 dot is given in kilogram per minute, this will be m1 dot into h1 minus h6 will be in kilojoule per minute. Okay, so this is a refracting effect. Okay, if you have to find COP, COP will be refracting effect by work, right? So work can be written as work is taking place in two stage, right? Since we have two compressor, work is taking place in two stage. So it will be H2 minus H1 and H4 minus H3, right? So work can be written as H2 minus H1 and plus H4 minus H3. But students, very important difference is that the mass flowing through the low pressure compressor is not same as the mass flowing through high pressure compressor. So mass flowing through low pressure compressor is M1 dot, and through high pressure compressor is M2 dot. Very important. So if you write COP, it will be of the form m1 dot into what is h1 minus h6 by m1 dot into h2 minus h1 plus m2 dot h4 minus h3. Okay, so h6 can be written as hf5, right? Because h6 is same, the value of enthalpy is same as that of hf5 because this is isenthalpic process. So you can substitute here with hf5. Okay, now a very important, a crucial problem we are encountering here is with m2 dot. We may not have an idea of m2 dot, but in questions and all, the mass given in the usually given in the questions will be the mass that is flowing through the evaporator. So the mass flowing through the evaporator is, through evaporator only m1 dot is flowing, and you may not, m1 dot is given, so that you have the value of m1 dot, but you may not have an idea of m2 dot. So how to find m2 dot? So in order to find m2 dot, we have to consider this particular figure. Okay, so here you can see that, so m1 is entering to the liquid intercooler, and m2 is leaving the intercooler. So m3 is getting evaporated and joined with the m1. So m1 plus m3 equal to m2. So this equation you know. Okay, this equation you know. But this won't be enough for finding m2 because here m3 is there. m3 also you don't know. You have no idea about m3. So you will require one more equation. For that equation, you have to apply the conservation of energy in this particular figure, or for you have to apply conservation of energy in this case of liquid intercooler. So conservation of energy equation here means you have to write like heat 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 taken by liquid intercooler will be equal to heat given by given by liquid intercooler. So what do you mean by heat taken by liquid intercooler? So a stream is coming, a stream is entering the liquid intercooler means this particular heat m1 into h2. H2 means the state of vapor entering the liquid cooler is 2. So the enthalpy corresponding to state 2 is h2. Mass of the liquid, mass of this particular stream is m1. So m1 h2 is entering, so this is heat taken by liquid, and another stream also is entering here. So it is, the entering stream is this one from condenser or expansion valve. So what is the mass of that stream? M2. What is the state of that, enthalpy of that stream? So its state is 5. The state is 5, and so that state 5 means its enthalpy will be H5 or HF5. So M2 and HF5 is also entering. So total heat taken by liquid intercool is M1H2 plus M2H5. Similarly, two streams are exiting from this intercooler, right? So to evaporator it exits in the state 6 and the mass will be m1. So m1 into h6 will be the enthalpy of that particular, or the heat accompanied with that particular stream. So here m2 into h3 is m2 h3 exits in this direction. So mass is m2 and the state is 3. So h3 will be the enthalpy corresponding to that particular stream. So m2 h3. So I can write enthalpy, the energy equation like m1 into h6 plus m2 into h3 equal to m2 into hf5 plus m1 into h2, right? So I can write m2 as, if I rearrange m2 as m1 into h2 minus h6 by, so I have taken this particular term to right hand side and this to left hand side. So h3 minus hf5 will be in the denominator. So m2 can be written as m1 into h2 minus h6 by h3 minus hf5. Okay. So if you want to find m3, the value of m3, you just subtract m1 from m2, m2 minus m1. So m2 can be written as m1 into h2 minus hf5 by h3 minus hf5, because h6 and hf5 are same only, right? Here instead of h6 you can write hf5, because h3, hf5 and h6 are having the same value, because that is 5 to 6 is an isenthalpy process. So hf5 minus m1. So if you use this equation, you can find the value of m3. So sometimes in the question you may be asked to find the value of m3, or the amount of liquid evaporator in the liquid intercooler may be asked. So in that case you should know how to find the value of that particular amount. So this is the equation. So you have to apply the conservation of energy equation here. Okay. So you learn how to find m3 and you learn how to find m2. So you can substitute. For m2 here in the equation of COP. You can substitute for m2 as m1 into h2 minus hf5 by h3 minus hf5. So that is how you find what you find the COP of the system. Okay. So this is the equilibrium, thermal equilibrium, the case of thermal equilibrium for a liquid intercooler. So in thermal equilibrium, heat taken by liquid intercooler will be equal to heat given by liquid intercooler. Okay. So students, I just forgot to mention a very important aspect here. And so in this system, you can see that the expansion valve here is a floating valve type. So you can see a float valve here. So something is floating here. So what is the use of this floating valve? This because this float valve help to maintain the liquid level here at a constant level. So in order to maintain the liquid at a constant level, this floating valve is used. When this liquid, the amount of liquid is going below certain level, this float valve gets actuated and the expansion, the process of expansion get increased, so that more amount of liquid is generated, and this liquid, so that the liquid level in that liquid intercooler may be maintained at constant level itself. So that is the function of float valve. Okay, hope you have understood. Now we will move to another, the second type of two-stage compression. So here a two-stage compression with the water intercooler and liquid subcooler. So here students, you can see that from its initial state is 1. So from 1, here 1, you can see from 1 to 2, from 1 to 2, what is happening? Isentropic compression. And 2 to 3, what is happening? It is cooled using a water intercooler. 2 to 3, you can see here 2 to 3. So 2 to 3, the liquid, the vapor refrigerant is cooled. Actually, it is in superated condition. This superated vapor is a little bit cooled using by passing it through a water intercooler. So water intercooler is, we are using an external agent. This external agent is nothing but water. So using water, we are cooling it. We are cooling the superated vapor. In the previous case, we have cooled the superated vapor using the same vapor refrigerant coming from the condenser of that particular refrigeration system. So using the same refrigerant we have cooled. So that is why the that particular case was called liquid intercooler. But here we are using the word called water intercooler. So we are using an external agent, water as a as a as an aid to de-superheat. So de-superheat means we are cooling the superated vapor. So we are de-superheating that particular vapor, and again from 3 to 4 it is again isentropically compressed. From 4 to 5 condensation takes place at constant temperature. After 5 you can see a liquid subcooler is used. So after 5, so the process 5 to 6 is nothing but the high pressure, high temperature saturated liquid effluent is passed through a liquid subcooler, so that the temperature is again reduced to a certain extent, and after that 6 to 7 expansion valve, through the it is passed through the expansion valve, so that expansion takes place, and 7 to 1 evaporation. So why this undercooling or liquid subcooling is applied? Why? You have already learned that idea in the previous module. So if the liquid vapor, if the liquid refrigerant was expanded from this portion itself, the refrigeration effect that we may go to, the refrigeration effect that we may get to cool the refrigerator space will be only this much. Okay, only this much. But when it is subcooled, so it reaches the position 6 and then it is expanded, and now we have this much amount of refrigeration effect. So that is the importance of subcooling. So you can increase the refrigeration effect when you are applying subcooling to the liquid refrigerant coming from the condenser. Okay. So water intercooling. So what is water intercooling doing? Water intercooling reduces the work to be done in high pressure compressor system. How? How? Suppose if there is no water intercooling means from 2 to 3 you will be compressing it in this manner. Okay. So this amount of compression, the work required in this particular compression will be higher than this case. Suppose, okay, I will show you once more. Suppose from 2 to some 4 dash I am compressing without intercooling 2 to 4 dash. So work, so H4 dash minus H2 will be greater than H4 minus H3. So the work here will be higher than the work in this case. So students, naturally when you look at pH diagrams, this pH charts will be available in a reference data book. So you can see that suppose this is a pH diagram. So this is a pH diagram. From here to here I am compressing. Okay, compressing. So this is 1 2 3. I'm directly compressing in two stages without intercooling. Suppose from 1 to 2 I have compressed and I have intercooled to a 3 dash and again compressed to the same pressure level. Suppose H2 minus H1 plus H4 minus H3 dash. So adding this two will be lesser than adding this and this. So that is how pH diagram is. So what is how can you understand that particular concept means? These lines which are very close to this dry saturated line will have very less work. So the enthalpy difference between the points that are very close to this dry saturated line will be lower compared to some lines which are away from the dry saturated line. So these lines will have higher difference, a larger difference in enthalpy. These lines will have a lower difference. So that is why we are applying intercooling. So suppose I have compressed to this point and I have intercooled means I am adjusting the line or arranging the line or shifting the line towards the dry saturated line, so that we can reduce the work. So that is the idea of applying intercooling. Same is the case that the logic, same is the logic behind arranging or applying this liquid intercooler here. So from 2 to 3 I have intercooled, I have cooled this refrigerant superheated vapor so that I can reduce the work. So if I have not used the intercooler means the work will be higher. So it will be like this, and this difference will be higher than this plus this. So that is the idea of applying, or the logic behind applying the intercooler, whether it is water intercooler or liquid intercooler. That doesn't make any difference in case of decreasing the compressor. One thing is sure, whenever you apply a intercooler, whether it is water intercooler or the liquid intercooler, the work required in the compressor will definitely get reduced. Okay. So hope you have understood this particular uh, system also. Two-stage compression system with the water intercooler and a liquid subcooler. So here how can you write the refrigeration effect? Refrigeration effect is nothing but m1 into h1 minus h7, right? m1 into h1 minus h7. So here no two masses are there because only one mass is there. Same mass m1 is circulating through whole of the cycle. No two streams, no two different streams are here. So m1 into h1 minus h7, right? h7, right? So but h7 is equal to h6 itself because that is a isenthalpic process. So m1 dot into h1 minus h6 because h6 equal to h7 itself. And what will be the work? Work will be m1 dot into initially h2 minus h1 minus h1 plus m1 dot into now h4 minus h3 sir, h4 minus h3. Okay, so this is the work. So in order to get COP, you just find the ratio of refracting effect to the work. So there is no much complexity in this case because there are no different streams coming together or leaving from a particular component. This water intercooler and liquid subcooler is using external air. Maybe here also some water. I mean, this liquid can be any other liquid other than this refrigerant. A water intercooler here, water is as external agent. So there is no mixing of streams. Okay, there is no mixing of the streams. They are they are not getting directly in contact with the refrigerant. They are not mixed. So while taking the mass, you don't have to confuse as in the case of liquid subcooler, liquid intercooler. So there a mixing is taking place, right? So there you can see here mixing is taking place, right? But in the second case there is no mixing, so while taking the mass there are no different streams, so it is even simpler considered to the first case. So hope you have understood these two concepts, and there are more type of multiple stage compression systems are coming, and we will discuss it in detail in the coming sessions. And in the examination point of view, no much numerical problems are asked in the university questions. So you have to make sure that the theory is okay, the concept is okay for you. So usually these theory parts are asked in this particular module. You don't have to worry about the numerical problems. Okay. So with this, I will stop this session. Thank you.